Where is Vinay? Professor Dale. Very good morning. Welcome, sir. Our Ali sir has joined.
Just write it down. Write it down.
Namaskar.
Rajiv. Rajiv.
Yes, sir.
Ali sir and director sir will join shortly, right?
Yes, sir.
Yeah.
Yes.
So you can start.
We are ready.
We'll start.
We are ready, sir. We are ready.
Yeah.
Yeah.
And
Good morning. Yeah. Good morning, Professor Dan.
Good morning.
And rather good afternoon in your place.
Right. When is my talk at 2:30?
Yes, your time 2:30. Yes.
Right. So this is beginning the ceremony.
Sir, good morning, sir.
Hello.
yes, Professor Dane, you please. What is your query?
Oh, my talk is at 2:30, right? Half an hour from now.
Your talk is today only. After this function, after this inaugural function, your talk will start.
Okay, so I'll switch off my microphone.
Now you can switch off. You will be requested to speak few words. Fine. Then director sir has joined, sir. If you permit, we will start.
Yes, please.
Rajiv, start.
Thank you, sir. Good morning and a very warm welcome to our chief guest and Honorable Director of National Institute of Technology, Silchar, Professor Sivaji Bandyopadhyay. Guests of honor, Dr. J.P. Mishra, HOD, Electrical Engineering Department, NIT Silchar. Professor Upendra Kumar, Institute Coordinator, Spark, NIT Silchar. Professor Muqaddas Ali Ahmed, Dean Research and Consultancy, NIT Silchar. Our special guest and plenary speaker, Professor Dan Cho from Seoul National University, South Korea. Deans, heads of various departments, faculty members of NIT Silchar, and my dear participants. Greetings to one and all. I hope all of you are well and safe in this pandemic situation. On behalf of the entire organizing team, I, Nabanita Adhikari, welcome you all, and I would like to express my heartfelt gratitude for your presence in this international virtual symposium on Control, Communication and Embedded System for Robotics, Soccer 2020, organized jointly by NIT Silchar, India and Dalhousie University, Canada, under the banner of SPARK, MHRD, Government of India. Once again, I'd like to welcome all the dignitaries and participants gathered here and wish you a good day. Now, I request Dr. Rajit Dey, convener of the program, to initiate the EDR lighting to mark the beginning of the ceremony. Sir, please.
शुभं कुरु त्वं कल्याणं आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणं आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तुते ओ दीपब्रह्मरूपस्थं ज्योतिषां प्रभुरव्ययः ओ दीपब्रह्मरूपस्थं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश्च मतिं स्वच्छामि मे सदा रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् यस्य तिष्ठे गृहे दीपः तस्य नास्ति दरिद्रता शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः
Thank you, sir. Now, I would like to invite our beloved HOD, Department of Electrical Engineering, Dr. J.P. Mishra, sir, for the welcome address. Sir, please.
Thank you, Dr. Navanita. Very good morning, one and all present here. Honorable Chief Guest, Director, National Institute of Technology, Silchar, Professor Shivaji Bandyopadhyay. Honorable Special Guest and Plenary Speaker, Professor Dongil Dancho, Department of Electrical and Computer Engineering, Seoul National University, Seoul, South Korea. Respected Dean, Research and Consultancy, NIT Silchar, Professor M. Ali Ahmad. Respected Coordinator, Spark, NIT Silchar, Professor U. Kumar, Civil Engineering Department, NIT Silchar. Respected Technical Chair of Symposium, Professor B.K. Roy, Electrical Engineering Department, NIT Silchar. Esteemed faculty colleagues, dear participants from different teaching institutions as well as industries all across India and abroad, I extend my warm welcome to all in this inaugural ceremony of 2 days virtual international symposium on control, communication and embedded system for robotics, Soccer 2020, being organized in joint collaboration of the National Institute of Technology, Silchar, India and the Dalhousie University, Canada, through the scheme for promotion of academic and research collaboration SPARK project under the Ministry of Human Resource Development, MHRD, Government of India. As cited by the coordinator, the main objective of this Soccer 2020 is the control, wireless communication and development of embedded system for robotic applications. We know that the control plays a very vital role in the areas of robotic, including robot-robot and human-robot cooperation, in various dynamic scenarios of applications like space, surgery, rehabilitation, micro machine, entertainment, underwater, civil engineering, professional and domestic services, security, etc. Due to the changing communication infrastructure and technologies, it is highly desirable these days to propagate control commands through wireless communication channel or medium. Therefore, the inclusion of wireless communication for control of robotic systems process possesses serious challenges to the performance of the control system. This requires cutting-edge technologies to develop and test control algorithms for a robotic system or application under such communication environment. Furthermore, for real-time implementation of the control through present-day communication network also requires realizable and scalable embedded design. Presently, we have our guest of honor and first plenary speaker, Professor Dong-il Dan Cho from the Department of Electrical and Computer Engineering, Seoul National University, Seoul, South Korea, where he is currently the director of Biomimetic Robotic Research Center also. His current research interests include microfabrication, microsensors, and controls. I thank you for joining this inauguration function of this symposium and also for accepting our invitation to deliver plenary talk with your intense expertise to make this symposium more interesting and informative. I hope this symposium may provide a unique opportunity for all the participants to present and discuss research and development work pertaining to the development of intelligent and nonlinear control and embedded control for robotic systems emerging for non-standard operating environment. My thanks to both the conveners of the symposium, Dr. Rajiv De, as well as Dr. Navanita Adhikari of the Electrical Engineering Department, National Institute of Technology, Silchar, India, who are also the PI and co-PI of the SPARK project, under which the symposium is being organized by them. My best wishes to the entire organizing committee for a grand success of the symposium. Thank you all again. Over to Navanita Adhikari.
Thank you, sir. Now, I would like to invite the convener of Soccer 2020, Dr. Rajiv De, to say a few words about the symposium.
Respected Director NIT Silchar, Professor Shivaji Bandyopadhyay, Chief Guest and Patron of the Symposium. Our today's special guest for the inaugural ceremony, Professor Dan Cho from Seoul National University, South Korea. Dean Research and Consultancy, Professor M. Ali Ahmed, Dr. J.P. Misra, HOD Electrical Engineering, Coordinator Spark Project for NIT Silchar, Professor U. Kumar, Organizing Chair of the Symposium, Professor N.B. Dev Chaudhary, Technical Chair of the Symposium, Professor B.K. Roy, all the Deans of NIT Silchar, all the head of the departments of NIT Silchar, my esteemed colleagues, registered participants, and my dear student friends. Good morning to one and all present here in this virtual platform. And good afternoon to Professor Dan Cho back in South Korea. I welcome you all to the inauguration ceremony of Virtual International Symposium on Control, Communication, and Embedded System for Robotics, which stands for Soccer 2020. This symposium is a part of our commitment in the bilateral SPARK project with Dalhousie University, Canada, which is supported by Ministry of Human Resource and Development, Government of India. Today, we could not have our PI from Canada, Professor Jason Gu, here because of the time difference between India and Canada. But he will be joining us in the afternoon session or the early morning in Canada with his plenary speech. Our SPARK project was sanctioned under innovation-driven project targeted towards development of robust control strategy for bilateral teleoperation with communication delay and experimental investigation for stroke patient rehabilitation. So this was a part of assistive robotic technology for the benefit of human mankind situated across the geographical boundaries. So our HOD has already given a brief about and the focus of this SOCR. So as the name suggests for this symposium, we tried to create an interdisciplinary platform to bring control researchers, communication researchers, embedded system researchers in one platform, because robotic applications cannot be done only by an control engineers or only by an embedded. So it is an integration of these three major disciplines. So we wanted to provide a platform here to these three. These are our three primary focus of this conference, and of course the interplay between these three disciplines, making this symposium truly an interdisciplinary nature of symposium. I also hope that this conference will also open up avenues for many of us to take up research work on the various aspects of cyber physical system and its application too. So as we are very hopeful with our collaborator in Canada that we will try to have a teleoperation robot situated in the laboratory in Dalhousie University and the control laboratory in NIT Silchar. So we want to see that across the geographical boundaries, can we really have a robotic control? So breaking the barrier, geographical barrier, and trying to get a control in two different labs situated so far distant. So that is actually the target of our project. And the technical quality and management of this symposium will be discussed by my colleague, Professor B.K. Roy, in details, who is the technical chair of the symposium. So lastly, I conclude by welcoming you all once again to the symposium. Thank you.
Thank you, sir. Now, may I request Professor Upendra Kumar, Institute Coordinator, SPARC, NIT Silchar, to share his views about the program.
Very good morning to the Excellence, Honorable Director, Professor Sivaji Pandopadhyay, Dean Research and Consultancy, Professor M.A. Ahmed, Head of the Department Electrical Engineering, Dr. J.P. Mishra, Technical Chair, Professor B.K. Roy, Professor Dan Chow, Seoul National University, all expert speakers, faculty members, and participants. It is my great pleasure and honor to welcome you all in the inaugural ceremony of SOCR 2020. This symposium is a part of SPARC project of Dr. Rajiv De and Dr. Nabanita Adhikari, which is in collaboration with international PI Professor Jason and Professor Haure of Dalhousie University. SPARC is a MHRD Government of India project aims at improving the research ecosystem of India's higher educational institutes by facilitating academic and research collaboration between Indian institutes and the best institutions in the world, from 28 selected nations, to jointly solve problems of national and or international relevance. Currently, we are having 4 such projects at NIT Silchar. We have also applied for 14 numbers of new SPARC projects for the year 2020-21, and we are hoping to get good numbers of projects. Finally, I'd like to thank all of you for participating in the program. Special thanks to all the expert speakers for giving their valuable time for the symposium. Thanks to SPARC MHRD for the support. Thanks to our director sir for giving his constant support and encouragement. I also thank our young faculty coordinators, Dr. Rajiv De and Dr. Nabanita Adhikari, for organizing Soccer 2020. Let us make the Soccer 2020 a great success. Thank you all. Have a nice day. Over to Dr. Nabanita.
Thank you very much, sir. Now, I would like to invite Professor Binoy Krishna Roy, Technical Chair, Soccer 2020, to address the gathering. So please.
So, very good morning to one and all present here. Our Honorable Director and Chief Guest of today's function, Professor Sivaji Bandyopadhyay. Our first plenary speaker, Professor Den. A better introductions will be a man from academics with 140 US and Korean patent holder. Respected Dean RC, Professor Ali Ahmed. My coordinator, Spark, Professor Upendra Kumar. Our HOD, Dr. JP Misra, the convener of today's organization, today's Soccer 2020, and my respected colleagues, dear participants, ladies and gentlemen, a warm welcome to you all. Since we have now introduced the purpose of this conference, the background of the conference, I will directly jump into some technical issues that we have taken care for this conference. This symposium was supposed to be held in June 2020, but because of pandemic, we have to defer it, and finally we are having it on virtual mode. Now, we tried our best to control the quality of the conference, as it is reflected that we have got 90 papers and we have accepted 32 out of 90 papers, and thereby our acceptance rate is 35% roughly. In the whole process, nearly 160 reviewers helped us to come to this conclusion. We have 4 plenary sessions. All these 4 plenary sessions will be delivered by renowned expert in this field, and we are very happy to see one of them here with us, Professor Chow. And as I said, the Professor Chow has 140 US and Korean patents in his credit. So that is the caliber of plenary speakers that we have in the symposium. We have 7 technical sessions in 5 different tracks. These tracks are control theory, control applications in robotics, computational paradigm in robotics, innovation in robotic system, electrical vehicle, compact and efficient power infrastructure for robotics systems. We have tried our best to select the best paper so that the outcome of this symposium is really a success one, and all these accepted paper after their extended version will be published in a book. So I mutual communication and mutual collaboration with others. With this, I conclude. Thank you. Back to Nabanita.
Thank you, sir. Thank you very much for your kind words. May I now request our first plenary speaker and special guest, Professor Dong Il Dan Cho of Seoul National University, South Korea, to address the gathering. So please.
It's a great honor to attend the inaugural soccer symposium. I've been to India only once before, and I was looking forward to going to India again, but that couldn't happen this time. And I'm so happy that you're doing it virtually so that I could still see you on the TV monitor here from Korea. And based on what you just said, it looks like you put in a tremendous effort to get this going, and the highest control of quality of papers being submitted and presented. And I congratulate you on this wonderful collaboration with Dalhousie University in Canada. And I hope you obtain very fruitful results and continue this soccer symposium in the future. And I hope you have a great couple of days ahead of you to exchange scientific and technical information together. Thank you very much.
Thank you very much, Professor Cho. So now I would request Professor Muqaddas Ali Ahmed Sir, Dean RNC of NIT Silchar, to share his views about the program.
Yeah, thank you, Navanita. Good morning to all present in this virtual symposium. Honorable Director NIT Silchar, Professor Sivaji Bandyopadhyay, Professor Dong Il Dan Chow from Seoul, HOD Electrical Engineering Department, Dr. J.P. Mishra, Professor U. Kumar, the Coordinator of Spark Project, Professor B.K. Roy, the Technical Chair of the Symposium, Dr. Rajiv Dey and Navanita Odhikari, the PI and co-PI of the project, all the authors of the paper, and all the plenary speakers. I, on behalf of the institution, welcome you all to this Symposium SOCAR 2020. NIT Silchar is sprawling a campus, green campus with about 600 acres of land. We have about 6 BTech programs, 15 MTech programs, 3 MSc programs, 1 MBA program, and PhD in all disciplines. We have at present about 4,000 plus situation is going on. In our institution, we are running full online mode of teaching and research. So nothing is pandemic for our institution. Everything is going on as usual. About the national and international project, NIT Silchar is having about 50 plus high-value national and international projects, out of which 4 number of Spark projects are also going on. As you know, nowadays it is the days of interdisciplinary research and collaborative research, and that is the result of this in this aspect is nothing but the Spark project, which is internationally collaborating project, basically, supported by Ministry of Human Resource, Government of India. So for this particular project, as you have already understood, I hope the researcher will carry forward and help the all community to come across the objective of the robotics for medical research successfully. I'll request all the researchers and all the authors of the paper to carry out the research such that our world or the community is benefited from our research. Not only we are gaining the number of publication and patent. We should now, it is the high time that we should convert our knowledge to dollar, basically. We have to go for product and patenting, as Professor Dang Il Dancho has done about 140 number of patents all over the globe. I congratulate Professor Don Chiu, and I request our young researchers to follow people like Professor Don Il Chow, so that we can also follow his path and have number of patents and product and support the all to our best possible way. With this, I wish this Silchar 2020 a very successful one. Thank you very much. Over to Adhika Navanita. Thank you.
Thank you, sir, for your motivating words. Now, I would like to invite our Honorable Director, Sir, Professor Sivaji Bandyopadhyay, who is also the patron of this symposium, to address the gathering. Sir, please.
Yeah. Good afternoon to Professor Dancho from Seoul National University. Good morning to my colleagues at India, to all my colleagues at other institutes in the country. Wishing a good day to all the other participants of submissions and the paper acceptance. So a good number of people, they have joined the YouTube webcast of this Silchar 2020 International Symposium on Control, Communication and Embedded System for Robotics. Now, already we understand that is, had the pandemic not been there, it would have been not possible to organize such a program in such a large scale. So, like say Professor Cho from Seoul joining at this time, and say other colleagues at this place. So sometimes say we try to identify the positive aspect or positive light in every situation. But I do wish when the situation, this current pandemic part will be over, I do invite Professor Cho to our campus, and to initiate collaborative activities with our colleagues here at NIT Silchar. Now at National Institute of Technology Silchar, we put focus on research and innovation in all our activities. We have undergraduate research council to put or to inculcate the research culture among the undergraduate students. And as our Dean Research Consultancy has already said, that is for say around 200 faculty members in the institute. Currently, we have around 800 PhD students. In the last 2.5 years, we have almost doubled the number of PhD students. The idea is that is, as the world is progressing very fast, technology is changing so rapidly. So we need to work in more and more interdisciplinary areas. And for that, we need good quality PhD students and good number at the same time. Now, when we talk about research and innovation, we focus on translational research that we do in our laboratory, so that gets translated into products in the industry, and finally it comes to the benefit of the society. We focus on interdisciplinary research. That is the kind of symposium or the Spark project on behalf of which the symposium is being held on control, communication and embedded systems. Because research in today's world is interdisciplinary. And interdisciplinary research basically means it has to be collaborative also, not only at the institute level, but also at the national and at the global level as well. Then internationalization is another key, because as we interact or collaborate with international experts, so we get to know about the innovative problems that are being tackled by the experts across the globe. And then only an innovative solution to such innovative problems are possible. And obviously, finally, in the industry, in the technical research, so they are playing a role. And we try to collaborate with the industry who are more focused towards the research. Now, in our pursuit for research and innovation, we do participate in the different ranking, and at the national level, we are moderately placed at rank position 46 among engineering colleges, 94th among overall institutions. In the innovation ranking at the national level, we are in the rank band of 11 to 25. And at the world university ranking, for the first time, we are placed in the Times Higher Education World University Ranking 2021 in the rank band of 801 to 1000. Now, when we talk about these ranking figures or ranking positions, what we basically try to focus on is that we consider this to reassess our position, where our strength lies, where are our weaknesses, where are our opportunities that lie ahead, and what are the challenges that we need to face, so that our journey towards excellence that we do in the collaborative manner, in the most international collaborative manner as much as possible, and with the kind of experts like, say, Professor Cho, with 140 number of US and Korean patents taken together. So that is really a great kind of collaborations for us. And I do wish that this Symposium Soccer 2020, it is not only is a result of collaboration with Dalhousie University, Canada, as part of the SPARK project, but more and more international collaborations in future are going to come up in the area of robotics, control, and communications. I wish the symposium a grand success. Thank you.
Thank you, sir, for your inspirational words and support from the beginning of this program. So now we are approaching the end of this inauguration ceremony. And I'd like to hand over the mic to Dr. Rajiv Dey.
So I request my co-convener, Dr. Navanita, to propose the vote of thanks.
Thank you very much, sir. It is my privilege and immense pleasure to propose the vote of thanks in this international virtual symposium on control, communication, and embedded system for robotics, Soccer 2020. On behalf of the organizing team, I express my sincere thanks to our Honorable Director, Sir, Professor Shivaji Bandyopadhyay. Sir, we thank you for your constant encouragement and for allowing us to apply for the SPARK Project Fund, which has led to this event. We also thank you for supporting us by facilitating the purchase of laboratory equipment related to the project, thus boosting our morale and inspiring us to contribute to the society through research and development. This event would not have been possible without your support and motivation. Thank you, sir. I extend my gratitude to our current HOD, Electrical Engineering, Dr. J.P. Mishra, sir, and previous HOD, Professor Nalin Bihari Dev Chaudhary, sir, for their support and encouragement throughout the project and the preparation of the symposium. I extend my gratitude to our guest of honor, Dean, Research and Consultancy, Professor Muqaddas Ali Ahmed, sir, and Professor Upendra Kumar, sir, Institute Coordinator, SPARK, and IT Silchar, for their motivation, suggestion, and support for conducting this symposium. Thank you, sir. I'd also like to express my sincere thanks to all the invited guests in this ceremony, including all the deans and HODs of the departments, for directly and indirectly helping and supporting us for the smooth conduction of the symposium. I'd like to extend my sincere thanks and gratitude to our eminent guest speaker, Professor Dan Cho of Seoul National University, South Korea, for sharing his valuable time with us and enlightening us with his lecture. We are eagerly looking forward to your plenary talk. I would also like to express my sincere thanks to Professor Binoy Krishna Roy, Technical Chair of SOCCER 2020, for his support and advice throughout the process. Sir, despite your busy schedule, you were always there with us in every step, starting from your help in publicizing the symposium to the paper review process to meticulous planning of all the technical sessions. Thank you. I would like to thank this opportunity to thank the entire organizing team for their constant support and encouragement. I would like to thank the publicity chair and co-chairs along with the website and IT committee for dedicatedly publicizing SOCCER 2020 in India and all around the globe. I would also like to thank our media partner, Tech Counselors, for their professional assistance in publicizing the symposium over social media. I'd also like to take this opportunity to thank all the authors who have submitted their papers to SOCCER 2020. I'd like to thank our registration chair and co-chairs for their efficient and smooth conduction of the entire registration process. I would also especially like to thank the publication team led by the publication chair, Dr. Prashant Roy, and all the publication co-chairs for their relentless efforts in the review process. I would like to take this opportunity to thank all the reviewers who have helped us by offering their valuable reviews of the papers submitted to the symposium. Now, I'd like to extend my gratitude to all the plenary speakers who have graciously accepted our invitation for sharing their time and knowledge through the plenary sessions. I would also like to extend my thanks to all the chairs and co-chairs for accepting our invitations. We are thankful for the team of PI and collaborators in the project from Dalhousie University, Canada, Professor Jason Gu, Dr. Umar Farooq, and Mohammed Usman Assad for their constant help and support. On behalf of the organizing team, I would like to convey my thanks to IIT Kharagpur SPARC, Ministry of Human Resource Development, Government of India, for granting this project and establishing our link with the Dalhousie University, Canada. I'd also like to thank Springer for accepting our proposal to publish the papers presented in SOCCER 2020 as book chapters in a research monograph. Now, I'd like to thank the members of the Central Computer Center, NIT Silchar, especially Dr. Ripon Padgiri, Dr. Naresh Babu, and Mr. Manas Pratim Mahanta, for their support throughout the preparation of SOCCER 2020 and streaming the program in YouTube channel. I'd like to extend my gratitude toward the state section of NIT Silchar, especially Dr. Dulal Das, for providing us with the UPS and electrical connections to maintain the uninterrupted power supply for the smooth conduction of the symposium. I'd also like to extend my thanks to the account section of NIT Silchar for their support regarding the financial matters. Now, I would like to thank our student volunteers, Mr. Nalini Prasad Mahanti and Samuel, for helping us in different stages of the symposium. I'd also like to thank NIT Silchar and the Department of Electrical Engineering overall for supporting us in every way. Last but not the least, I'd like to extend my heartiest thanks to the convener, Dr. Rajiv Dey, for his tireless efforts in the successful conduction of this symposium. Sir, SOCCER 2020 has been your vision, and your relentless efforts and motivation has made it possible for all of us today to gather here at this inauguration. I'm thankful for having the privilege of working with you, and thank you, sir, for giving me this opportunity to convey the vote of thanks. In case I have forgotten to mention anyone personally here, I would like to thank each and every person who has helped and supported us in bringing this vision of SOCCER 2020 to a reality. Thank you, everyone. Now, may I request our director, sir, to announce the beginning of the symposium.
Yeah, I declare the beginning of the International Symposium on Control, Communication and Embedded System for Robotics, SOCCER 2020. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
So we will start the plenary talk Professor Dan Cho very soon. So the entire session will be chaired by Professor Binoy Krishna Roy. So I'd like to request Professor Roy to welcome Professor Cho and to start our plenary session.
Navanita, should you start it now? Navanita,
Yes, sir. We can start now. Over to
Or-
you, sir. Now I'm handing the.
it will start at 11:30. What is the original time?
So we are actually running a bit late, so we can start the session now.
So to start the session, I would like to welcome Professor B.K. Roy, Professor, Department of Electrical Engineering, NIT Silchar. Professor B.K. Roy did his master's and PhD from IIT Kharagpur, India. His primary focus of work in earlier days was definitely control theory, but over the years with his experience, he has worked in many domains of control theory. As far as I know him as a colleague, his current area of research is network control system, and mostly he is known in our country and outside for nonlinear dynamics and chaos and nonlinear systems. So I welcome Professor Binay Krishna Roy as the chair of the session, and over to you, Professor Roy, to conduct the session.
So thank you, Rajiv. Now, I have this privilege and honor that they have given me the opportunity to chair the plenary session 1. Our speaker, who is present with us for last more than half an hour, we have heard him. A little introductions that we have said about him, that a man who has 140 patents in his credit. So if I go a little back, Professor Dancho received his Bachelor of Science in Mechanical Engineering from Carnegie Mellon University, Pittsburgh, and MS and PhD degree from MIT Cambridge in USA. Now he was assistant professor in the Department of Mechanical Aerospace Engineering at Princeton University, USA from 1987 to 93. So since 93, he is associated with his present university, and in fact, in 93 itself, he joined as a professor in the Department of Electrical and Computer Engineering at Seoul National University in Korea. He is director of Biomimetic Robot Research Center at Seoul National University. He has co-authored more than 140 international journals, and he has 140 US and Korean patents in his credit. He has served on the editorial board of many international journals. Currently, he is senior editor of IEEE Journal of MEMS, IFAX Mechatronics. He served as president of Institute of Control, Robotics and Systems, technical board member of IFAC, council member of IFAC, BOG member of IEEE Control System Society. I'm happy to say that Professor Dencho is currently the president-elect of International Federation of Automatic Control. Congratulations to you, sir. And he has received many awards in his credit. A few of them are listed here. He received IFAC Outstanding Service Award in 2011, the ICROS Award in 2015. He also received awards from the Minister of Information and Communication of Korea in 2006 and the Prime Minister of Korea in 2008. He is an elected member of National Academy of Engineering of Korea. This is his short introduction. So with these short introductions, we have understood that an academic man can also have, that 140 numbers of patent. This is something, as our director sir also said, is encouraging and motivating for all of us to follow him. With these brief words, I welcome you, sir, and to start your presentation on biomimetic robots, current status and future directions. In this talk, Professor Dan will speak on the state of art of biomimicry robot. Present state, this is representing ground biomimetic robots, aerial biomimetic robots, and underwater biomimetic robots. Further, technological limitations of the present biomimetic robots and direction of development that need to be taken to overcome them will also be discussed by Professor Den. So I welcome Professor Den. Now stage is for you. Please go ahead, sir.
Thank you very much for this grandiose introduction. It makes me bigger than what I really am.
We can see you, Professor Dan. We can see your screen.
Yes.
Yeah.
Well, thank you very much for invitation to SACO 2020, and really thank you for the wonderful introduction. I heard the most commonly spoken word today so far was 140 patents. It was by accident, but I have 140 transactions and journal papers and 140 patents. I got interested in patents mainly because I met a colleague when I was a professor at Princeton University. He was a crazy scientist. He invented. I was 29 years old when I became a professor there, and he was 65. He was just about retiring, and he invented a little, little rubber piece that you put on the tennis racket to observe vibration so that you don't get the tennis elbow. He invented the device, and he taught me how to write patents. And so I got interested in writing patents. So I wrote a few of them all by myself initially. Then I had university write patents with patent attorneys later on. But it's been fun. And in Korea, they require, when you accept government projects, they require that you write so many patents and so many papers. So, the two sort of went hand in hand. And patents for the sake of writing patents really is not that so great. I think you have to write usable, applicable patents. In my lifetime, I did 3 startup companies, and eventually the third one, I was able to sell it, M&A, and I basically used many of my patents, and I've also licensed a good 1/3 of the patents written to small companies and large companies, so that they actually help the mankind used in certain products. It's been a very fruitful that I ran into this crazy scientist, and his name is Enoch Durbin, and I thank Enoch for getting me started in patents. Now, as you heard in the introduction, I think the theme of SACA is interdisciplinary research, and you try to bring in entrepreneurship as well. And my research from the start was all interdisciplinary research. My undergraduate education was mechanical engineering. Then I went to MIT and still in mechanical engineering, but I decided to work on controls, and I did sliding mode control for my PhD. My PhD is in '88, but I was basically finished in 1987. So in 1987, I became a faculty member of Princeton University and ran into Enoch. And also one of my mentors called Rob Stengel, who introduced me to microelectromechanical systems. He informed me then there is a new field that's coming up. It's called, there wasn't a name before, it's dealing with small things. So I got interested in microelectromechanical systems. So ever since I am doing both controls and MEMS and applying it to various disciplines, including manufacturing and robotics. And my PhD supervisor was the late Carl Hedrick, who got me into nonlinear control and sliding mode control. Well, we live in one globe, and in technical areas, IEEE and IFAC, we basically divide into regions, the globe into 3 pieces. India and Korea both belong to Asia Pacific region, and this green arrow indicates Silchar, and this arrow indicates Korea. We are only 2 inches apart, but in internet today, we are in the same space. The technology is really wonderful. And out of this 4.06 billion in this region, 1.4 is in India, I think. Oh, by the way, my first student was from India. He graduated from IIT Madras. He came to Princeton, my first PhD. And since I've had a student from IIT Kanpur, and at Seoul National University, I've had 2 PhDs from IIT Delhi who came to do postdoc with me. And I have a very high regard for the technology and scientific minds of Indians. Most of you have not been to Seoul. This is Seoul. This tower is the new landmark building in Korea. It's 555 meters tall, 123-story building. The downtown area and the city hall is right behind this mountain. And I live right about here, and just off the picture. And my university is about here. My university is within the boundaries of Seoul. Oops. And this is what my university looks like. We have 17,000 undergraduates, 12,000 graduates, and 2,200 professors. We have full disciplines, liberal arts, natural sciences, engineering, and all. And we have 3 campuses. The main campus is 115,000 square meters, which is in the picture. Right now, I'm sitting in a building here on the right corner. This is electrical engineering building, and we have an Institute of Control and Automation, and I'm sitting in this office right now. Before I start, I want to...
Is it in?
Yes?
Yeah, at the bottom, see, there is a pop-up. So yeah, you put it to stop, yeah. Stop sharing, yeah. Thank you. Go ahead, please.
Okay. Before I begin, I want to thank my students now and former students. I get together with my graduates once a year, and we have dinner together, and we tell each other how we've been doing for a year. And so far, I have about 100 graduates from my lab. Today's talk, I'll talk about biomimetic robots. It's something that I've been working on for 6 years now. My initial work was on automotive control. Then I did MEMS sensors, MEMS actuators. Then I did manufacturing robots, which I still do. And to the arsenal, I've added biomimetic robots 6 years ago. I'm the director of a center called Biomimetic Robot Research Center. It's funded by Defense Acquisition Program Administration and the Defense Agency for Defense Development to about $15.5 million. What is a robot? It started by Karol Čapek in 1920. It was a translated, it's a story, it's translated into 30 languages, and it comes from the Slavic language robota. Anytime you have an A at the end, that means plural, so robot, I guess, is a singular. The world's first robot was Electro by Westinghouse in 1939. In the 70s and 80s, we used to call it robot. Today, you don't call it robot, we say robot. And I just want to show you something here. This is really interesting mechanism. But it really is, it's really fancy. It looks like a robot, but it's not a robot. Robot needs to have brains. Robot needs to do things in its own with a cognition capability. Now, this is something I forgot to mention. I also work with cleaning robots. I've been doing cleaning robot research for almost 10 years. And I don't know if you can see it. I'm holding one right here. I use it in my office. This one is 7 years old. And I've actually developed some of the algorithms that go in the robot. And the LG has much newer robots now, but it has intelligence. It looks at the objects, and it avoids obstacles, and it avoids dangers, and it avoids running into things and damaging your furniture. Now, this is a cleaning machine. It's a vacuum, but it's a robot. It has autonomy. But this yellow car transformer, this is nothing more than just a fancy mechanicals. Okay, this is taken from my lab. This is a Vicon lab. You see 3 little dash robots. You see 3 little bird robots. This is radio controlled right now. There are 3 of my students are standing. They're doing radio control for these robots. We've added closed loop control algorithms to this later on, but this dash robot is very difficult to control, whereas this one is much easier to control. Now, these are toys, though. These are not really robots. These are toys. Now, a real biomimetic robot, one of the most famous one is this guy called Rex. It's developed by Boston Dynamics. They first introduced it in 1998, and now it's commercially available. And what it does is, before this, when we think about robot, we have a manufacturing robot, then we have manipulators that looks like human arms, then we have humanoids or bipeds that try to walk. But now when you expand the target to more animals and insects, then you can overcome the difficulties you have with just trying to mimic humans with 2 legs. Now, you cannot imagine having a robot going through this rough terrain with 2 legs. And this guy is very clever. Even if it flips, it runs like nothing happened. This is now commercially available. Biomimetic starts with Greek word bios and mimesis, and you know the meaning. You can see the screen. And we're trying to solve problems through nature by studying living things. So we use nature as a teacher, learn how to make robots that can rise and crawl, do all sorts of things. Until now, though, most biomimetic robots really only imitate the structure, imitate the motion. But the real attempts for making real robots doing cognition and control and communication and interface have been lacking, and that's what my center does. We make biomimetic robots, but we make computer languages suited just for biomimetic robots. We do cognition suitable for inexpensive robots, and we try to come up with communication and interface at a low cost. Research trends in biomimetic robots. You need to do various bioanalysis. You need to come up with materials, novel manufacturing techniques, and you also do multimodal robots that is doing more than one function, more than just walking, for example. And people try to do develop multifunctional parts to reduce weights. That's really the focus of this talk. I think this box is should be one higher, but the more important thing, I think, is intelligence and autonomy and communication and interfaces, and that's what majority of what my center does, because my center is in electrical and computer engineering. Unfortunately, I won't be able to talk too much about it today. Now, what's bioanalysis? First, you look at the insects very carefully. Take pictures, take close-up pictures, and see what it looks like. That's not enough, so you take the insects and animals and take it into a SEM, scanning electron microscope. This is baboon lizard or gecko. If you look at this part really carefully with a scanning electron microscope, you see it's made of a bundle of nanowires, and the nanowires have tree-looking branches like this. With a van der Waals force, this creates tremendous stiction force. People also use wind tunnel to study how insects fly. Of course, dissecting and looking at the physiology of animals and insects is a popular analysis technique. They take X-rays They even take MRIs using high-speed cameras to see how lizard leaps, and using 3D motion capture system. These are IR markers attached to dogs to study how animals move. And we're also looking at different materials to make robots. New materials that are stronger and more resilient and more robust and suitable for miniaturization, and also flexible materials so that you can handle fragile objects. For making tiny robots, we're also looking into MEMS technology and additive manufacturing and 3D printing. 4D printing also. 4D printing means you have a 3D printed structure that can change shape, so it becomes 4D. We also make biomimetic actuators. These are inchworm-like actuators that deforms and moves, but it has asymmetrical structure, so it moves forward. And this was done by our center. And some people are looking at some pneumatic actuators because electrical motors and hydraulic actuators have limited compliance. That, in other words, infinite stiffness. But pneumatic actuators are very compliant, like pneumatic tires that you use in cars. We are looking into making multimodal robots. Robots that can move on ground and fly at the same time, or crawl and jump. I'll show you some pictures later on. And this is a robot that can climb a wall and also fly. And these are robots that can fly and also go underwater. They call it flying fish. And these are amphibious robots that can crawl on the ground and then also swim underwater. Additive manufacturing has become a very popular research topic for biomimetic robots. This is a fold-up structure. You can make a robot from a fold-up structure. And if you think of origami, that's a Japanese art of folding things out of paper. You could fold things out of paper and plastics. And this is also made from the origami structure. This robot, it's an inchworm robot, and it weighs only 1 gram. I'll show you a movie of it later on. Now, how much time do I have? Do I have until
Please proceed.
Time? Okay.
Please proceed.
All right. These are some of the famous, well-known ground robots that I want to show you. And I was thinking today, since this is a soccer conference, you could probably make a robot that looks like a soccer ball. And you kick it, and later on becomes a robot. This pill body looks like a pill. It's made by a colleague in Korea at KAIST. It reminded me when I saw the title again and hit me, you could probably make a soccer robot. It's an idea for you. There are, can you count how many there are? 38. The first biomimetic robot, humanoid is a biomimetic robot. And when Honda, Japanese car company, developed a humanoid and announced it in 1986, it was really shocking. It was the first real walking humanoid robot, and it's a car company. They make automobiles, and they make a robot. They invested in science, I guess. And 5 years ago, DARPA had a DARPA Robotics Challenge, and eventually it was issued a couple of years before, and they went to first round and second round. And this DARPA Humanoid Challenge was won by a good friend of mine, Professor O from KAIST, and he won the contest. It was doing specific tasks, and Professor O is a really smart person. Most people try to just make a walking robot. He made a walking robot that can kneel, and on the wheel, it can move fast forward. And he won the challenge and also $1 million US. Now, Boston Dynamics is probably one of the most well-known in humanoid robots today. And 2011, they showed the humanoid robot. Today, they make humanoid robot that can jump and flip and do gymnastic movements. It can climb stairs. They've done really wonderful things. And Boston Dynamics trying to apply humanoid robot into commercial applications, and I think eventually they will succeed. And there are many other biped robots. This Digit by Agility Robotics USA is trying to. They are to be sold in 2020. I'm not sure if they have done it or not, but they are trying to do delivery robots based on this. Now, four-legged quadrupeds is another famous robot. This is made by also a good friend of mine, Professor Kim at MIT. It's a cheetah robot. Cheetah is fastest running animal. It runs up to 110 kilometers per hour. And he actually developed a robot later on that runs up to 60 miles per hour, so which is the same as the real cheetah. But lately, I think he got into a mini cheetah, and he issued a challenge, cheetah soccer challenge. But because of the pandemic, it never really took place. It's a 9-kilogram cheetah robot, a four-legged robot. It can fall, and you'll see it'll stand up on its own, just like the Rex, 6-legged. And it's very robust, very controllable, very flexible robot. Now, among four-legged robots, this big dog is the most famous. It runs on a gasoline engine, and it can run 24 hours. And it's developed for the military for carrying ammunitions and other supplies. And in Korea, we also have a four-legged robot. It was also funded by military. Sorry, this was funded by Industry Commerce Ministry. More cheetah robots. These cheetah robots can run really fast, and they've shown that they can control it to a good balance and make it run very fast. Other types of four-legged robot, and this one is a two-legged jumping robot. I have so many videos, I'll just move on fast. Kangaroo robot, a German company called Festo. They are making all sorts of ground, aerial, and underwater biomimetic robots. And their artwork is also really fantastic. It looks like a real kangaroo. You have a multi-blade robots, crawler type, and you have a four-legged robot, but this is Delta robot. Rex again from Boston Dynamics. Again, this is a commercial product now. And Professor Kakowski at Stanford, he developed this climbing lizard robot or gecko. Him with Carnegie Mellon's professor met in City. And I showed you the scanning electron picture before. They use nanowires for creating stiction force so that the robot can climb. And later they developed a climbing robot that can also detach and fly or glide down to ground. More climbing robot. And this one at the bottom, you can see it uses hands that bends and touches surface, and then to detach, it has to bend. It uses van der Waals force of nanowires, and nanowires are manufactured maybe 15-20 degrees slanted, so that it takes forces in one direction only, and in the other direction, the opposite direction, it doesn't take the force. But the force is enough to carry the weight of the robot. Here we go. That's the nanowire that they have developed. Comes from studying very closely using scanning electron microscope. Students at Professor Fearing's lab at UC Berkeley, this robot is made out of paper, and they developed a company called Dash Robotics. And Dash Robotics was in operation for a few years. They were bought out by a giant toy company called Mattel, and Mattel now makes Dash robots made of plastic, and they sell it as toys. And I have both 40 robots made of paper, and I forget how many, but a whole bunch of Dash robots made of plastic. And I reprogrammed the MCU of this Dash robot and implement a controller so that we can do directional control of Dash robot motion. This one is 8-legged, and this one is another jumping robot. And this is again German Festo, different types of 6-legged robot. These wires, I think, artwork. Their artwork is really fascinating. Now this is a Pillbot, and here we go. It deforms and it can climb, and you could probably make a soccer ball shaped robot that you can kick, and then when it lands, it'll transform into a robot and do funny, interesting things. Now this is made at our center, Biomimetic Robot Research Center. This is an inchworm. It weighs only 1.2 grams and 1.5 centimeters long, and it's made from a origami, folding structure. And this one here is a jumping robot. It's a flea. And this is really amazing. You can see this jump. It just jumped right now. It weighs only 1 gram. It's only 2 centimeters long, but it jumps 65 centimeters high. Some more robots by Festo. This is not a robot. They developed flexible actuator inspired by chameleon and used as a gripper to grip fragile objects, any shaped objects. And this is another very interesting Delta robot. And this uses gecko hands, nanowires, and it has enough force to lift this brick. This is a flying monkey. It walks. I don't know. It doesn't look like a monkey, but they call it flying monkey. and it's got rotors so it can fly. All right. Now, different funny little robots. In the interest of time, I'll skip some. This is a jumping robot developed at our center. This one crawls. It's multimodal. It crawls and jumps. Lots of interesting robots. This is a changing wheel diameter. You'll see with a smaller wheel diameter, it moves forward. Then when it expands, it can move faster. A tire company in Korea actually looked at this technology. Now you see the obstacle, you reduce the wheel size and you go underneath. And a tire company is trying to develop a diameter changing tire for mountain vehicles and for military use. Okay, I showed this transformer here again. I showed you a lot of robots, but to me, they're really fancy mechanicals. They don't really think yet. We need robots. I showed you a vacuum robot. It's like it's only a vacuum machine, but the vacuum machine thinks. So I think the vacuum robot is more close to a robot form that I like to see than just fancy materials. Of course, this vacuum robot, you can control it with internet, you can control it remote, all sorts of things. Now I'll show you some flying robots. Again, both of them are Festo. It looks so real, and you won't be able to spot them in the sky, and you'll just think that it's a real bird, unless your eyes are good enough to see the letters Festo. This nano hummingbird, this hummingbird also looks so real. It actually appeared in the movie, in the surveillance mission. And it's very well developed. It only weighs 19 grams, wingspan of 16.5 centimeters, and it can fly 6.7 meters per second. And that was developed 13 years ago. And we are also developing flying robots at our center. This is one developed by us. And we have a few more versions, but in the interest of time, I'll show you others' work as well. This is iBird. This is a bat robot or batbot. Again, this Festus, this is a butterfly robot. It's very fancy robot. I think these are still controlled by a radio frequency device. This is RoboBee, developed by Robert Wood from Harvard. It can jump, it can fly, and it only weighs 80 milligrams. And he gives great talks. When you get a chance, inviting him to give a talk would be very entertaining. This is a Bionic Opter by Festo. And more flying robots, flying and gliding. This is our center's version of flying robot. It weighs 6 grams. And this is a Dobe drone made by Northwestern University in China. And this is deployed in Chinese police. They used to track people. So this is also a commercial device. This Falcon robot, it looks so real. And these are all radio controlled, this bionic bird also. We also have a similar version that we're testing control functions and communication functions. In order to develop control and communication methods, you need a platform. So we also developed a robot that looks like that. These are more versions. There are a lot of people in the world who are developing these sort of robots, at least 20, 30 teams. Now, I'll show you this movie that I've taken in my lab. This is my Vicon laboratory. I've shown you a lot of flying birds, but I tell you, they're not so much different than this toy. And this toy is actually really wonderful. We take it apart, we study it. It was built very cleverly. We use it to test control and communication methods developed for biomimetic robots using this as a platform. You could buy this on the eBay for, I think it was $25 or $30 per toy. There are lots of underwater robots also, mimicking fish, jellyfish, snakes, and alligators type robots. These are fish robots. These really seem to work well. They look so real. You see this one on the top. It looks like a real fish, and you probably cannot even tell the difference if you see it next to each other, if you see it in life. We had a tragic accident in Korea about 4 years ago. There was a ship that sank, and almost 300 people died from the wreckage. And Korea also developed swimming robots, fish-type robots. We tried to deploy them, but the ship sank in an area with a very strong water current. The water speed there is 15 knots, or in ground speed, that'll be like 25 kilometers per hour. And the fishes just could not swim against the current. So these fishes work really well in the tank and are still water. But I don't think there's still fish robot that can work in high current environment. I'll show you one later on that works. These are also different types of fish robots. See this one? This is a robot, not a real fish. And this is a jellyfish-like robot. Again, this is a shark or penguin developed by Festo. Now, these snake robots are very interesting. They look a little yucky, but they can crawl and then they can swim on the water. You see, now it's entering the water, and these are, I think these are natural birds, and the birds think that this is not harmful and not a machine. Different types. This is really quite interesting. This is right now in a tank. This is developed by a very good friend of mine, Kristin Pedersen. She's in Norway, and she's done many plenary talks at IEEE, ACC, and IFAC World Congress. She also gives very nice talks. This is Mamba. This is an earlier version. She has a version called Eloom. She even has a company, and they actually make a snake robot that found a sunken Norwegian submarine that was sunk during the World War II. It was sunk in Russian Straits, and the water current there is really high. And the submarine has very small windows, and the Eloom was successfully used to in the mission to find the submarine. And they located the submarine, and they found the old sailors' corpse, and they were able to pull out the submarine and have the funerals for those who died in the submarine. That was 2 or 3 years ago, and I saw the movie in a closed talk, and it was really moving. And this robot can actually overcome very high current. Okay, I think I've taken up a lot of time. I started late, but I tried to speed up a little bit. Future works. I've shown you tons and tons of biomimetic robots. There are just so much research going on in the world, and there have been so much progress made in the last 10 years in biomimetic robots. And some of them look really, really impressive, and some of them are very efficient, and they do really well. And we are beginning to understand how to make them better. But now the biomimetic robots are capable of doing simple operation, or they just show they can move, but it's not really enough to carry out a specific mission. We need new methods to deploy them. We need new methods to interact with surroundings, and we need to improve operating time efficiency for low power and reduce weight. And we need better communication methods, Zigbee and Wi-Fi or LTE or 5G. They are too much energy consumption, and they require too much overhead for biomimetic robots. So my center is developing different communication methods for efficient dissemination of transmission of information. I'm sorry, this is in Korean. I know. I hold it. In 2018, the Winter Olympics was in Korea, and I don't know whether you saw it or not. The Winter Olympic Games. It was a very exciting Olympic Games. We also had Olympics for robots, and it was commissioned by the Ministry of Industry and Commerce, and several teams, several professors in Korea University developed skiing robots. It's autonomous. It's not radio controlled. It's a microprocessor with sensors. It almost looks like human. Whoa! 이날 5개의 깃발문을 모두 통과한 로봇은 8대 중 2대에 불과했습니다. 대부분의 로봇은 깃발에 부딪히거나 속도를 이기지 못하고 앞으로 고꾸라졌습니다. Controllability. 첫 대회라 아쉬운 부분은 있었지만 의미 있는 출발점이라는 평가가 나옵니다. Okay, there are 8 robots and 2 actually finished to the finish line. I think that is really something. We have robots that can look at the environment, look at the different color flags, and make the right turn and the left turn. using the vision camera and gyro sensors and accelerometers to control the motion and control the direction. So that was done in 2018, and I'm kind of sad because they don't keep funding this because I think we can scientifically and technologically learn a lot from exercises like this. Okay, this is my last slide. I want to advertise in 2026, by the time the pandemic would be over, and the IFAC World Congress, that's the largest control-related conference in the world. In 2017, when it was held in Toulouse, it was attended by 3,700 people. And in 2020, it was held in Berlin, but as you know, it was held virtually. The 2026 IFAC World Congress in August will be held in Busan. This is the second largest city in Seoul, in Korea. And these are real pictures, real buildings. There's a nice beach in this area, and the convention center is right here. And the you could actually work during the day and enjoy in the evening at the beach. There are hundreds of hotels on the beach, and it's only 20-25 minute walking distance. There's a subway that's 2 stops away, and it'll be a very enjoyable conference. So I invite all of you to submit papers in 2026 to IFAC World Congress. Thank you.
So, thank you, Professor Dane, for your usual excellent presentation, because I saw you in IIT Chennai in the last February, right? I was mesmerized with your presentation, and then you have done little ahead during the current presentation. Excellent presentation, excellent information, right?
Thank you.
Now I will request my colleagues, if they have got any queries, they can unmute themselves and they can ask their query to Professor Den. Dr. Rajiv.
Maybe it's lunchtime.
Yeah, Dr. Rajiv. Navunita. Am I not audible? Yes. Dr. Navunita.
You are audible, sir. You are audible. You are audible.
Yeah. Dr. Navunita, Dr. Rajiv.
Hello, sir. Yes.
No, what I'm asking, whether there is any query in the YouTube? In the chat
Sir,
box of YouTube?
any queries? There are no queries, sir.
Okay, fine. So I think, your presentation was so lucid. Your presentation was, so much interesting. And possibly my colleagues and other people who are in the YouTube mainly, they do not have any question to. So it is my opportunity to close up the session. So let me close the session with a little brief that you have said. You have given us a very nice survey of the actual products which are available in these 3 different kinds of robots, or rather 3 different kinds of use. It's ground, underground, and aerial biomimicry robot. So you have also shown in some places you mentioned, and I hope my colleagues and other participants, they have also noticed that there were some which were so small. In fact, it was in grams. For example, that omega bot, fine, omega bot. Just imagine, friends, that omega bot's weight 1.2 gram and his length is 1.5 centimeter. Just imagine, and it has got all control and it can jump up to 65 centimeters. Fine. So that is the kind of work which are going on or which has already been here in this field, right? Then we have heard good number of aerial robots, iBird, bellbot, butterfly robots, and we have, RoboBee, which just weight, I was imagining, we just weight 80 milligram. Am I correct, Professor Dan?
Yes, about that, yes.
It's 80 milligram, fine, and wingspan is of 3 centimeters. So that is the size of this and how crucial this will be, how precision, by which they have been making it. As Professor Dang has said, all these are being made in their lab only, including the design of sensors, including the design of actuators. Everything is made by them. Now, then we have gone for some examples of underwater, then robotic fish, and those pictures, if these pictures have been played, and if you are not said whether these are real or robotics, possibly it will be very difficult for us to distinguish. They appears to be so realistic, fine, and I hope so many challenges so many futures works has been displayed in the very last slide. And also here, Professor Dan has mentioned about that incident that had happened. And finally, what was realized that whatever underwater robots we have now, they have a real difficulty that they cannot work at high velocity of current. So therefore, this possibly is an open problem to all of you. Then you can try how you can make it work at high current. And then we have also seen that applications of different robots, for example, aerial robots, dope drone. This is something which is being used by Chinese police. We have Memba underwater snake. It was used to locate the submarine. Fine. This also we have seen, we have heard from Professor Den. And in future work, as Professor Dan has said, that just whatever has been done is not enough. What needs to be more is that robot must able to interact with the environment, with the surroundings, right? There is another very big challenge. That challenge is once we put something underwater or we place something aerial, so we should see that power consumption is as low as possible, so that it sustains in its autonomous mode to the larger extent, the larger time. So power reduction is another big challenge. How do you get those optimized output by reducing the power? And then finally, Professor Dan has shown us the very interesting, actually somehow I did not watch that, so therefore it was not in my memory. So that autonomous robots were in the playground. That was very interesting. And what was more interesting, that out of 8, 2 could reach to the destination. So therefore, these robots, they are not machine now, they are behaving like a human. So therefore, wherever they get obstacle, they have the power to avoid all the obstacles and finally reach to their destination. So it was an excellent presentation, and we could know a variety of robots, the whole span of biomimicking robots. And the way he presented, everywhere he has said, this is mimicking which rather, that natural phenomena. So that way also it was very interesting. And since we have also come to the, and also another thing, Professor Dan has started little late, but he could complete in 1 hour the time which was given to him. So thank you so much, Professor Dan. And finally, we wish to see you here in our campus, possibly in 2022. I will contact you. I will do the needful. We have been organizing IFEC we have been organizing one conference that is under the banner of IFEC. This is biannual conference what we have here in India. We call it ACDOS. We call it Accords. So Accords 2022. It will be held at NIT Silchar.
Oh.
So as you said, possibly we hope that by that time we can have our physical conferences. If we have it, then we will be extremely happy to see you here in our campus. And we will be extremely happy if we, my colleagues, participants, they get an opportunity to work with you on this particular field. And finally, I end, when you have said your regards for the technical mind of India. Thank you so much for your recognitions on the, the technical mind of our people here. So finally, I conclude with lots of thanks to you for accepting our offer and be present here since from the inauguration function to till now. And we are very happy, and we hope that we will have this relation that we have established. Will continue this relation in future also. With this, I conclude. Thank you very much, sir.
Thank you.
Thank you. So Rajiv, you can go for the announcement.
Yes, sir. Thank you very much. Thank you, Professor Cho. So we will now move on to our technical sessions, and this plenary session has now ended. Thank you, Professor Cho, very much for sharing your time, for sharing your presentations, and Professor Bikaroy, sir, thank you very much for conducting the session smoothly.
So thank you.
applied to the system, then satisfying the event condition 6, that is when where epsilon gets yes, and it is bounded by alpha plus capital psi. The capital psi is an integral term which is given here. When this practical sliding motion is achieved, after that the state trajectories are confined with the set BQ and BQ dot given by equation 10 and 11. Now we have shown that with this theorem we showed that the system is having practical sliding mode and the system states are near to the origin, and it is confined in some set or confined within some ball. To show that the control action is bounded, we have a proposition where we take the norm of the control and show that we have the control is bounded by equation 12. The inequality is always satisfied. To show that the important issue is in event triggered control is that there should be finite number of sampling in finite time. So the time between two events to occur or two samples should always be greater than 0. So if we have this system 1 with sliding variable 2 and the control 5 and event condition 6 is satisfied, then it can be shown that the inter-event execution time, that is the time between two samples, that is tk plus 1 minus tk, is given by delta tk, is always greater than alpha by rho 1 of alpha plus mu. Here rho 1 of alpha is a function of alpha and mu is a constant given here in equation 14. So we try to evaluate this control as with the help of a robotic manipulator system given in paper 3, and the parameters are given here. So it is a basically having q1 and q1, it belongs to R2. So we have a fourth order system and the initial conditions are chosen as this. We have for simulation we have chosen a disturbance of 0.1 amplitude with sinusoids having 3 and 4 sampling, having frequency 3 and 4, and the gains k1, k2 and k3 are chosen satisfying event condition 8 in theorem 1, and lambda 1 and lambda 2 are inverse of k1 and k2, that is 1 and 1 by 4, that is 0.25. And to get a good visualization of how event triggered sliding mode behaves, we have chosen a rather large amplitude of alpha, that is alpha is equal to 0.2. So here we have the sliding variable. So here we can see the sliding variable reaches to some bounded range, and this sliding trajectory doesn't go out of this bound. So this ensures that a practical sliding motion is established, after which the straight trajectories can be seen to be within some bound and are at vicinity of the origin. Similar observation can be made for the other states, that is the arm velocities. The control signal is shown here. So the time between two samples, that is the inter-event execution time, is plotted here, and here we can see that the first sample occurs just as we start the simulation, because the controller and the controller doesn't know exactly where the system initial conditions are. So we have a first sample at the first instance of simulation, after which we can see that the inter-event execution time is sort of scattered and is always greater than 0. That is, it has a Zeno-free solution. To understand the effect of the variable alpha, we tried a few simulations and we describe a few performance indices of event triggered control from paper 4, where we have SRMS, the RMS value of the sliding variable, U average, the control average of control effort, NUP is the number of control updates, that is given by this equation. So here FUP is the event flag. So whenever a event condition is violated, the event flag is set to 1, otherwise it is 0. NS is the total number of samples. So we have done the simulation for 25 seconds. So here you can see that for alpha is equal to 0, that is we have considered a time triggered case. In 25 seconds, we have a sampling period of 0.001. We have 25,000 samples or samples. Then when alpha is varied as increasing, we can see that the number of updates reduce. So the percentage reduction is given here. So you can see at alpha is equal to 0.01, we almost reduce the number of updates by 42%, and the average sampling time is given by 0.0017. But a very good thing to notice is that the RMS value with time triggered case and event triggered case are similar, and also the difference in average control is not very high. So with even with smaller values of alpha, we can match the performance of the time triggered case, but the reduction in the samples, the reductions in the control updates is quite large. Means we are using less number of updates, which results in less number of communication between the plant and the controller. Once we go for higher value of alpha, we can see that the reduction is high, but there is deterioration in the RMS value of the sliding variable and also the average value of the control. So I'll conclude here with that the event triggered integral sliding mode controller with input saturation has been proposed with this paper. An unique event triggered mechanism has been designed. This is a bit different from the traditional sliding mode design, event triggered sliding mode designs, and the reachability has been shown. And instead of a practical stability, instead of a ideal stability, practical stability of the system states are shown that it is within some ball. So, also we have shown that the inter-event execution time is greater than 0, which ensures a xeno-free behavior of the system. Simulations show that it is effective. Here are the references. Thank you.
Thank you, Krishanu, for the presentation. And I welcome the participants to ask their questions to Krishanu if they have some. Krishanu, I would request you to, if it is possible, to put on your video so the participants can see you and get acquainted with your face. Yeah. So the participants can ask their questions. So if there is an option of raising hands, otherwise you can simply ask the question. Okay, so it seems that there is no question from the participant side. So I will try to ask some question.
Yes, sir.
So can you go to that slide last but one, I think, where you have tabulated the AS, RMS and all those things?
Mm-hmm.
Hmm.
Yes.
Not this one.
Okay.
Where,
Okay.
yeah,
Alpha.
yeah, this one. Yes. So it is. We can see that this with this alpha parameter changing. So somewhere we are getting some deterioration. But is it for this particular system that for alpha equals to 2 or 0.2 or 0.3 we are seeing such deterioration?
No,
suppose
sir,
I change the system to something else, then where would be the deterioration? So is it dependent on the also on the system? And is there a study on what is the good value of alpha to be chosen? Something like that?
Alpha choice is dependent on the application. So if I want a very precise value of the states, means I want to confine the states to very close to the origin, then alpha has to be chosen small. Then when I'll choose alpha small, automatically what will happen that the number of updates will rise, but also the performance of tracking, you will say that it will get a better tracking. And this is true for every event triggered case till now what I have studied, that if we give a larger amplitude in the event design parameter, automatically the number of updates, because it is nothing but a function which grows with time. So whenever the threshold value is reached, it samples, and again this goes to 0, and then again it grows. So if I give this a bigger band, it will take larger time to grow. But the
Hmm.
control will be held constant in between that two samples, so you will get a poorer performance in terms of tracking.
Hmm.
That
Okay.
is it.
Also, can you go to the question, your equation number 13, where you are,
Yes.
yes, this equation delta tk. So we want this inter-event time. This is the inter-event time, right?
Yes,
So
sir.
that should be finite. So if
Yes.
you say that this is greater than some quantity,
Hmm.
then does it make it finite? Because greater than some finite number can be anything, right?
No, it should be greater than 0. That it should not be like Zeno behavior, that in some finite time I am getting infinite number of switching.
No, I'm just concerned that this delta tk, that is a sampling between two events
Hmm.
or sampling two events, you have some quantity like alpha by rho 1 alpha plus mu. So it will come out to be some
Scalar.
value, some quantity it will come out to be.
Hmm.
So your delta tk would be greater than that. That I understand.
Hmm.
But how much greater? It can be like infinite also, because greater than some value is possibly it can become infinite also, isn't it so? So for a finite, when we want to understand that something is finite, we try to put a upper cap there so that it is between 0 and that value, that we understand.
I got your point, sir, but in the literature, what I have found that it is done in this way only, that they put a lower bound on the inter-event sampling, and it can be any higher value. Yes.
Then perhaps it is there is some implicit understanding that it cannot go to infinite for some reason that you need to
Yes.
understand. What is that reason?
Actually, sir, what the event condition is, suppose I come here, this is the event condition 6, and this where epsilon function is defined in 7. So when so what will happen is that if I take the derivative of where epsilon, it will say how this will grow. And this is implicit, I think, that this quantity will not be 0, because we cannot go and find q1 and q dot is equal to 0, because we are inside a ball, and in this ball it can go anywhere. So this quantity will not be 0, I guess. So that's why it's
Okay, so I think you can also clear your doubts later on.
okay.
And actually, I will end with a question, and
Yes.
perhaps you can find it can give you some more things to look into. But suppose the event does not happen at all, because it has become steady and all, so error is not this quantity is not increasing. So in that case, there will be no more sampling, right? So what is the situation happening there? So you can think about this thing, and probably there is an answer. I'm not an expert in this, so these questions came to my mind as I was listening to your talk. So probably you can find the answers to these things.
If q and q dot are at some constant, means they will go to 0 and get constant, then there is no need of control only, because when disturbance acts, then these two will grow in some way, and then only we need to take care of the system. This is means need based sampling.
Okay, so there is a contribution of the disturbance factor that comes into play. Okay.
Yeah.
Okay, thank you for the presentation.
Thank
And I guess if there are no more questions, then we can move on to the next presentation. So Sandeep Jana is pictured here. Is he here, Sandeep?
Soham sir.
Yes.
Sir, I have a question.
Yeah, you have a
right?
question. Okay. Yes, sure.
Krishna, how you have to select the values of K1, K2, K3 for your robot manipulator?
Okay, so I'll just share the slides one more. So the first K3 gets derived from the reachability condition that has to be met. So actually, I have not added the proofs. You can find in very good papers of Abhishek Behra and Bandyopadhyay sir. They have shown it very simply that first you have to choose the gains in such a way that you get a reachability condition is met. Means I enter and hit the sliding manifold s is equal to 0. That so that's why we have chosen this big theorem. Means we have added stability of the sliding variable and also the states, because
My
all the
question is, Krishna, I'm getting your
Okay.
point. My question is, how do you select that values? K1 equals to 2 and 3 like that one. Have you chosen arbitrarily or something?
No, sir. I have chosen according to this. Means I have chosen alpha first, and I have assumed that dm, the maximum bound of disturbance, is this. The maximum bound gm is this, and I have chosen beta is means after that beta comes into the picture. So in that way, I have chosen by choosing K3, then K2, then K1 can be any scalar, means scalar value greater than 0.
Okay. My last question is, you are saying that you are going to address some actuator saturation,
Yes,
but unable to see where you have to handle the actuator saturation.
Actuator saturation is given here, sir. In this proposition 1, we have shown that U is less than some finite quantity root of n, K1, K2, K3, where n is the dimension of the system.
Okay.
Sir.
Thank you, sir. Thank you, Krishnanu.
Yes, sir.
That's all about my question.
Yes, I guess Dr. Prashant Roy has a query.
Yeah, I have a simple query actually. Mr. Krishanu, can you please just briefly, in 1 or 2 sentences, highlight that what is the exact novel contribution of you in this paper?
Sir, the main novel contribution is I have tried to implement the previous controller in the one of the papers of I don't remember his name. So this
I mean, implement in the sense, did you put it in some real system? Okay.
No, sir. We have tried for simulation only. It was integral sliding mode was designed for normal continuous time system with continuous sliding mode. We have designed it in terms of event triggered sliding mode and how the gain conditions are different in event triggered sliding mode. That is, we have shown.
Okay, I got it. Just one more query. That is, can you go to your control signals? There is a slide where you have shown the control signals.
1 minute, sir. I'll start presenting once. Yes, sir.
Yeah, somewhere here. Yeah. This control signal, actually, I am wondering whether this control signal, especially control signal 2, whether it will be implementable in the real practical system, because it has too much high frequency content. So can you highlight this issue?
Sir, for practical systems, we can use, instead of the sine term, signum function, we can use some 10 hyperbolic or equivalent saturation function.
I mean, if you could do the same practice in simulation, then possibly you could have got an idea also, because how this is going to affect your output. Because if you sacrifice little bit of control signal, high frequency component, possibly something is going to affect your output also.
I guess, sir.
And one more thing.
Smoother, I guess.
Yeah. Please continue.
I think we will get a bit more smoother.
Now you will get a smoother output, smoother control signal using that, but at the cost of something actually. So that price. Anyway, you can think it of later. And the last one from my side is there is a disturbance you have chosen. 0.1 sine 3t. Yeah. So is there any specific reason to choose the frequency as 3 and 4?
No,
Or
sir,
it
that's
was
randomly.
randomly? Okay, because this you should choose carefully actually, because for different frequency of disturbance, system will respond differently.
Sir, actually, if this D I have chosen is bounded, I don't know that. So
No, see,
anyway, if it is some
okay.
okay, sir.
It may be fine. I don't know. So you maybe you please check it from your side.
Sure, sir.
That's a suggestion from me.
Yes,
I think I have finished from my side.
Okay.
Shom sir, over to you.
Yes, thank you. So I guess there are no further questions because no one has put their name in chat. So Prishanu, thank you for your presentation.
Thank you.
And carry on your work in this direction. It's a very nice and upcoming field. And now I would call upon Sandeep Jana. So is he ready with his presentation? So let me just confirm with him. Sandeep, are you here? Sandeep, are you here? So I could see Sandeep sometime back.
Yes, sir. Hello.
Yeah,
Hello.
Sandeep.
Yes.
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 Yes, you are audible. So I will introduce your paper, and after that you can start your presentation. So you'll be having 15 minutes time for each presentation, and after that, after each presentation, it will be followed by some question and answer. Okay. So Sandeep Jana is going to present. The title of the paper is Performance Evaluation of Adaptive Dither Control Frameworks for Nonlinear Piezo Actuator. Authors of the paper are Sandeep Jana, Dr. Saikat Kumar Shom, Dr. Arpita Mukherjee, and Dr. Partho Bhattacharjee. So Sandeep, you can start your presentation now.
Okay, sir. Good afternoon, everyone. Myself Sandeep Jana, Project JRF and ACSIR PhD student from CSIR Central Mechanical Engineering Research Institute. So first, I would like to thank the conference team giving me an opportunity to present my research work. I am going to present my paper works, the performance evolution of adaptive dither control framework for nonlinear piezo actuator. Actually, I am working a project. It's a Indo-French collaborative project, piezoelectric actuator system for automotive transfer system. We have developed a electrical driver circuit for piezoelectric actuator based inch motor to actuate or slide the seat of the driver's seat of the car. So it is the project partner is the Central Suklek University, Laurent Daniels, and in CSI CMRI Saikat Kumar Shom, senior scientist of Central Mechanical Engineering Institute, and the Horacia, the industrial partner, is there. So these are the contents which I will be discussing. Introduction, objective, RMS error comparison, parameter sensitivity test, performance against the external disturbances, mix amplitude and mix frequency input test, and the set point tracking with impulse disturbances, and the step input with impulse disturbances. Now, piezoelectric actuators are gradually playing an important role in precision positioning application, like micro positioning, nano positioning, due to their fine resolution and fast response, have no electromagnetic interference, and high torque, low power consumption, and safe locking at rest. However, the existence of the hysteresis, key behavior, and parametric variation, external disturbances, this makes a big influence on their positioning accuracy. So that we have developed a controller of piezo actuator, and hysteresis model are very necessary or meaningful to control the piezo actuator systems. So main objective is that we have developed the Dither controller, which is specially used for the control of nonlinear application through the relatively simple and computationally inexpensive logic. Dither means it is a user-defined noise of specific dosage which is reduce the system's nonlinearities and can enhance the system performance. And it is a mainly a high frequency signal or low frequency signal which has been injected in the control system. This research focus on the performance of evolution of different adaptive Dither control framework in the piezo actuator system. The result mainly suggests that the Dither controller, adaptive Dither controller, which is better than the traditional feed-forward controller and feedback with feed-forward controller or piezoelectric actuation system under several disturbances. So in this slide, it is a RMS error comparison. The table shows that the error comparison of different controller, where C1 is that feed-forward traditional controller, and C2 and error is the RMS error is 6.67 nanometers, and C2 is that the cascaded feed traditional forward and feed forward controller, and the error value is calculated is 0.26315 nanometers, and C3 is present the cascade feed traditional forward and feedback discrete Dither controller, which has the RMS error 2.23277 nanometers, and the C4 presents the cascaded feed forward and feedback voltage Dither controller, which has the RMS error 0.23627 nanometers, and finally we have developed the adaptive voltage Dither controller, which has least error like 0.23628 compared the other traditional feed forward controller. So in the picture, this figure shows the tracking performance plot or different adaptive controller with sinusoidal input response. In the zoom view of the picture, it is shown that the adaptive voltage Dither has the better tracking performance with the input. Input is a black one is the input. Is the adaptive voltage Dither controller. The tracking performance is near about the input side, input of the controller. So it is a better performance than other traditional controllers. And parameter sensitivity test is undertaken to observe the performance of the adaptive controller against the parameter variation. The plan parameter variation of the piezo of the model of the piezo actuator plan MDKT. This is a MDKT. It is a first we have modeled the piezo actuator input signal different amplitude and frequency, and from the output response we have identified the planned parameter of the piezo actuator system. This is a second order spring marks damper system mainly. The MDKT, this is a planned parameter variation. We have been varied the plan -2 ±2% and ±5% of the planned parameter variation, and we have get the RMS error are presented in table 1.1 1.2. It can be observed that the adaptive voltage Dither controller is the adaptive voltage Dither controller is better compensation of the parameter uncertainty than feedback with feed forward controller. Now we have performed the controller against the external disturbances external disturbances, Gaussian noise, which has been fed in the input side as a process noise, and second as a measurement noise toward the planned output. And the Gaussian noise variance from the 10 into e to the minus 22 to 10 into 10 to the minus 29. It is observed that the C5 means the adaptive voltage Dither controller has the least average error, and then the C2 is a feedback and feed forward controllers. The figure, this figure is shown as a schematic error plot with the sinusoidal wave input and external measurement noise. Gaussian is the variance is 10 to the minus 15. And in the zoom view of this picture is shown that adaptive voltage Dither is a green color is the better than the traditional feed-forward controller is shown in the figure. So now we have different input wave signal and varying amplitude and frequency have been applied to the piezo actuator system. The amplitude of the input wave signal has been varied from 0 to 10 micron, shown in the figure, 0 to 10 micron, and frequency varying from 0.25 to 1 hertz. It is seen that the particular amplitude, the error increases with the increase in the frequency of the input. In the table, we have seen that the error of the C1 is the controller is 6.31 nanometers, and in adaptive voltage ether controller is 0.30703 is a nanometers. Is very low if you compare with the feedback controller, traditional feedback controller. We have performed the disturbances set point tracking with impulse disturbances. The impulse disturbances width of 20 seconds is injected in the output of the plant parameter, output of the control systems, where we have seen that the adaptive voltage ether systems is a green one. Is noticed that it has the least settling time of the 20.44 seconds, and the traditional feed forward and feedback controller, which has 21.31 seconds, settles. So, however, the response has some undershoot is there with the and some have some oscillations. We have performed the similar nature of controller performance is observed for the system when subject to step input with impulse disturbance. Input as a step and the disturbance is an impulse. So the controller, adaptive voltage ether controller, has a better tracking performance, and settling time is very low than the traditional feed-forward controllers. So now I am concluding. A comparison of performance of different ether-based controller has been carried out in different conditions. The performance evolution suggests that the controller performance better under certain circumstances, like parameter sensitivity tested and performance against the external disturbances. Set point tracking with disturbance outperforming the others can be chosen depending upon the application. So adaptive voltage ether we have developed, which shows the best performance over the parameter sensitivity test and the external disturbance like impulse disturbance and set point tracking. These are the references.
Okay, thank you, Sandeep Jana, for the presentation. And I call upon the participants and the audience to ask their queries if they have any. You can also write down your name in the chat and I will call you one by one. So just having a brief, having a roundup of the understanding. So here you are actually comparing several several controllers for the piezoelectric system. So is this comparison done on an actual system, or is it a simulation based comparison you have done?
First, we have modeled the experimentally modeling the piezo actuator systems. Then we have done in the MATLAB Simulink, where different control logic has been developed, and these are the simulation results. Actually,
you have not applied it to the actual system from where you have made the model.
Yes, we have modeled the system, actual model in piezo systems experimentally by we have applied the input signal like different magnitude, different amplitude, and different frequency signal. We have from this data we have.
So you have modeled, you have identified the system basically. So you have a piezoelectric system. Yes, from there you have identified the model. Now you have made the controllers for that model. Now these results that you are showing, are they the simulation results? That means, are they the controllers applied on the model, or they are controllers applied on the actual system?
controls are applied on the it's a model in
Model one.
simulink.
So
Oh, yes.
just the query is this: since you already have the system with you and you have made the model out of the system, why did not you apply the controllers on the actual system also? So you could have
Okay.
got the actual understanding of how it works.
Yeah.
Okay.
So, can I speak? Good morning, Mr. Soham, Dr. Soham.
Yes,
Yeah.
Dr. Saikat.
Yeah. So actually, the modeling has been done. Initially, we had taken the plant, and as he had said, we had done the modeling to identify the plant parameters. So after that, the system has been simulated. These comparison results which he is showing not simulation tables. After that, we're taking the best controller and we are implementing on the actual system in DSpace hardware. So that is still in
Yeah.
process.
So that is still in process. So you have not reported that result.
No, in this paper it has not been reported yet.
Okay.
So actually,
okay.
this paper, what he is presenting is focusing on deeper-based controllers. So this actually, as per the requirement, was they required some simple, which is controller, which is computationally inexpensive. So this basically refers to inducing some amount of noise of a particular dosage to control the system parameters. So this concept has been used earlier also, like in ADC, and it has been seen that inoculation of a particular external disturbance does increase the system SNR instead of reducing. So we just worked upon that domain. So we after the modeling, we found out two topologies. One is displacement dither and then voltage dither. So after that, we combined them also like cascaded displacement and voltage dither. Then we went on to some advancements like individually making these laws adaptive in nature. So after that, so there in this slide, he has presented the adaptive voltage dither. So this is it, comparing the adaptive voltage dither, the what is gone up to the maximum level, and then comparing it with existing traditional controls.
So actually, probably it would have been better if the dither control framework could have been shown, because the audience are not familiar with the theoretical, like algorithmic equations and all, which are there in the dither control. So that framework could have been shown in a slide, probably. And this is my observation.
Sandeep, do you have a MATLAB model? If you can, you show it.
In the paper I have.
No, in the model, MATLAB model in your laptop.
No problem. No problem. Dr. Prashanto Roy has a query. Let him ask the query, and we will further move on to the other presentations. Dr. Prashanto Roy.
Yeah, thank you, sir. Mr. Sandeep, I have a small query. You have chosen a frequency signal to get the response, I guess.
Yes.
Can you please go to that signal? Not
This
here.
one.
After that, I forgot the slide number actually. Yeah, this one. So that
This one.
mixed amplitude, mixed frequency signal. That one.
Yes. This one.
No, not that one.
Mixed.
It's in your screen. It's showing close to, yeah, this one. Mixed amplitude, mixed frequency input test.
Okay. This is the
now
input.
I have no, not this
and
one.
The impulse disturbances signal.
Multi-frequency,
multi-amplitude. Slide number 10, probably.
Yes.
Slide number 10.
Yes.
Yeah, mixed amplitude, mixed frequency input test. Yes. So, I mean, is there any basis to choose the amplitude and the frequency?
Yes. No, I have basically no. I have put in the input as 0 to 10 micron amplitude varies and 0.25 to 1 hertz. So, if you increase the frequency, then the output signal of the
no, my question is different. My question is little different. Actually, my query was that amplitude is fine. Maybe your system accept that amount of magnitude of the signal. But that frequency 0.5 to 1 hertz, why it is not from 0.25 to 5 hertz? So that was my query basically.
No, you can vary the frequency 0.25. I will take that 0.25 on hertz. If I increase frequency beyond beyond the 100 hertz, then the system response may be changed in the piezoelectric
No,
system.
Sandeep, the question sir is asking is that why did you particularly choose 0.25 to 1 hertz? Any specific reason for this limit, or it is generalized?
No, it is generalized, but if we increase the frequency much more, then it will change the system behaviors.
No, I mean,
Sir,
how can you?
actually, we are testing it for a range of frequency. So for our application, the range was from around 0.5 to 0.75 hertz. So for that, we have taken a small buffer and increased, started a below low and continued to 1 hertz. So that was the range of our requirement, and this amplitude also in the range of microns. So with this test range, we wanted to check how the control works. So this is the test input which has been given to the controller, and the system performs how the system responds that was observed.
Okay, got it, got it. So just one more query, that is that C1, C2, C3, C4, C5, those 5 control structure, do you have the block diagram? Because it is difficult to figure it out from the names, because there are multiple structures available for these names.
Yes. Yes, sir, I have.
Okay, it's fine, no issues. So Dr. Shoham, I think I have finished from my side. You may please continue.
Okay, thank you. So I believe there is no further questions on this presentation. Sandeep, you are the next presenter also. So you can pull up your next presentation slide while I introduce the paper. So the title of the paper is Comparative Performance Study of Different Controllers for Nonlinear Piezoelectric Stacked Actuator. And the authors are Sandeep Jana, Dr. Saikat Kumar Shom, Dr. Arpita Mukherjee, and Dr. Partho Bhattacharjee. So, Sandeep, you can start your presentation.
Okay, sir. Thank you very much. This is the extension work of the previous work which I have discussed. This is a comparative and performance study of different controller for nonlinear piezoactuator systems. So these are my contents we will be discussing. It's the RMS zero comparison parameter sensitivity test, performance against extra disturbances, behavior of different controllers, mix amplitude, mix frequency input test, set point tracking with impulse disturbances, and step input with impulse disturbances. So these are the basic things why we are using piezoelectric actuator. We gradually playing important roles, and we have some advantages likely fast and precise response, have no electromagnetic interference, and have high torque and low power consumption, and some have some demerit also. Is the hysteresis, creep, vibration, parametric variation, and external disturbances. The main objective is that we have developed the modified internal model control have been widely used in compensation of hysteresis and creep vibration of piezoelectric actuator. This research focus on comparative analysis of 4 controllers, namely modified internal model control, recursive least square estimator, and the traditional feed-forward and feedback feed-forward controllers. Result shows that the which controller is effective under what scenario, and that enhance the overall precision positioning efficiency of the systems. And the RMS table shows the RMS error of the controller. Here we have seen the C1 is a feed forward controller, and C2 is the cascaded feed traditional forward controller, and the C3 is the recursive least square estimator controller, and C4 is the modified internal model control. And the tracking response of the controller, a different adaptive controller with sinusoidal input response, we have checked the tracking performance of the modified IMC controller and RSLE controller with the compare with the traditional feed-forward controller. So we have seen that the modified IMC controller is the EOL1 is the better tracking performance than other controllers. So we have done also sensitivity test in the modified IMC controller, where we have we have been varied the plan parameter -2 +-2% to +-5% of the plan of the model MDKT, and then we have seen that it is observed that the earlier that modified RMC controller is the best RMS tracking error if we compare other controllers. So now we have performed the modified RMC controller with the other controller, basic traditional controller, feed forward and feedback controller. Against the external disturbances, we have used the Gaussian noise as a input side, as a process noise, and second as a measurement noise toward the plan output. The Gaussian noise is varied from the 10 to -5 to 10 to -29. So the controller, the modified RMC controller, the average error is less than the feedback controller or traditional feed forward controllers. These are the Gaussian noise as a process noise, input side noise, and this Gaussian noise as a measurement noise disturbance is the output of the plant. And error plot analysis of error plot with sinusoidal input, external disturbances of noisy environment has been studied, where modified RMC controller has the performed better in noisy environment than the other controllers like feed forward controller and RLSC controllers. So we have studied different amplitude, same type of different input wave signal like varying amplitude and frequency have been applied to the piezo systems, and the displacement is varied 0 to 10 micrometer, and the frequency varying from 0.25 to 1 hertz. It is seen that the modified RMC controller has a least RMS error compared with the feed forward controller and feedback controller. And set point tracking also performed against the external impulse disturbances with of 20 seconds. The feed forward controller settles at 21.31 seconds is rate 1, and the overshoot the RLSC recursive controller settles 26.9 seconds, and modified RMC controller is noticed have more larger settling time, about 32.5 seconds. We have performed the similar nature of controller is observed when the subjected to the step input with the impulse disturbances. The controller can be arranged in order of feedback controller is better, have settles less time than the modified RMC controller and the RLSC controller. So I am concluding this study is focused mainly comparative analysis of two prominent classes control of visuality actuator. Here we have developed the modified RMC controller, which has better performance than other traditional controller, feed forward and feedback controller. And modified RMC controller is observed to lend considerable improvement in performance of sinusoidal motion tracking and parameter uncertainty. And RLSC shows a very good performance of disturbance rejection of external Gaussian noise, both as a applied as a input side as a process noise, and the output of the plan as a measurement noise. So traditional feed forward controller has the least settling time with respect to the set point tracking only with the impulse disturbances. So these are my references.
Okay, Sandeep, I would request you to switch on your video once so that all of us come to know you. And so as I understand that this is the same system that you have taken in the earlier presentation. However, you are comparing some different other controllers.
Yes,
and here modified IMC controller you have tried to compare with the other existing traditional controllers to compare the performances. So the natural question that comes to my mind is why you have not compared the Dither controller also here with the modified IMC?
Hello, sir. So sorry, sir. Can you repeat the question? I am
My
not hearing.
question is,
I am not getting the question. Hello.
You have compared different controllers and with the MIMC controller, right? Modified IMC controller.
Yes.
Now, in the earlier
Yes, sir.
presentation, you had compared the traditional controllers with the Dither controller.
Yes.
Right. So
Right.
why did not you compare the Dither and the MIMC also?
Okay, because the modified IMC controller, which is the different between the adaptive voltage Dither controller and the feed-forward controllers. It's have different control structure. If I apply the piezo actuator systems, it response is different in different cases. We have applied the different condition, different load application. We have used different type of controllers. So modified IMC controller is the better if you implement in the experimentally, but in Dither controller, adaptive Dither controller, which has been used, design is very tough in the experimentally.
Okay, so that brings the question then, what is the utility of the Dither controller if you cannot implement it in experimentally? And the other question is that you are saying that in this MIMC you have implemented in the actual system,
yes,
or these are also simulation results?
These are the simulation results. We have tried in real time also. We have tried.
Those results are not yet reported.
Not yet. This is simulation results. And in adaptive voltage control is better for noisy. We have just noise of the specified dosage, which reduce the system non-linearities. Mainly, we have enhanced the system performance and can eliminate the non-linearities of the systems. We have used adaptive voltage Dither controls.
Yes, sir. Coming to your first question, so why we have not compared Dither with MIMC? So it certainly should have been done, but just for actually all these individual domains, Dither control, modified IMC, and RLSC, individually they have been tested for their efficiencies. But however, in this paper, what we are specifically comparing these two. So we are not proposing any of them, but we are comparing the and doing an analysis which is better. So that we could have compared with Dither, but somehow Dither we chose to be standalone and compared with the existing one, and even the RLSC and FIMC we have compared them to be standalone and compared with the existing. But certainly amongst them also we could have compared. Yes.
Okay, so any other query from anyone else?
Yes, sir. Small one. Hello, Mr. Sandeep. Can you hear me?
Yes, sir. I can hear.
So, just a small query. That is, you have used modify IMC, right?
Yes, yes.
In each, what way it is modified?
In IMC controller is the plan parameter. We have used a process model, and then we have process the plan model. After that, we have induced the process model to feed into the feedback side. You have used in the feedback. We have the process model has been used.
I cannot be a little more specific actually. I mean, what is there in IMC, in modified IMC, which is not there in the usual conventional IMC structure?
Yes. It is some difference. It is the output of the plant can be fed to the input side, process plant, which has been connected to the input side.
Sandeep, there are 3 blocks. One is control block, one is plant model, one is nominal plant model.
Yes.
So from existing IMC control, the question of sir is asking what modification you have done, where the loop you have changed. You explain that loop.
In the process model, I have changed the parameters from the actual plan. And
Okay, so sir, actually, I'll just tell you. So in the normal IMC model, we have first a control model, and then a loop branches to a plant model, and we have nominal plant model below that. So within the loop, we are having the plant and the nominal plant model. But in this modification, what we have done is that we have placed the nominal plant model along with the control. So we have made a feedback to the opposite side. So what advantages proposes is that we do not have two additional blocks. So there is a reduction in the hardware complexity and the controller logic, because ultimately upon this, it gives us equivalent PID control block. So we can replace this MIMC controller by a simple PID block, adjusting the gains obviously, followed by the plant model. So it comes in a direct, reduces the complexity.
Yes, sir. Thank you. And just I have a small suggestion that I mean, in your paper, if the block diagram could have been available, then
Absolutely, yes, this would have been much clearer.
then
Actually,
possibly easy to
Chandra, I
understand.
think he has referred the papers where they have been published individually, but even in the slide, it should have been kept. Otherwise, these questions are very natural.
Yes, yes. Anyway, thank you, sir.
Yeah, welcome.
Dr. Shom, sir, I have
Yeah.
finished from my side. It is over to you again.
Yes. So I'll just make a comment that even for normal IMC, the controller actually can be framed as a PID. It doesn't require any modification on the normal IMC block, normal IMC structure. With that normal IMC structure, whatever you design, it can be reframed as a PID controller. So in modified IMC, there should be something else actually, which is there. So perhaps the block diagram would have explained it better, but since we don't have it, we can't go into a discussion on that. So with that, I think we have all the presentations of this session are done. So I thank the presenters, Krishanu and Sandeep, for presenting in this session, as well as all the audience who are present here for attending this session. And Dr. Prashanto Roy and Dr. Abhat Pati were the co-chairs, and I also thank them for being there for support. And with that, I think we can conclude the session. If I have missed anything, please, Dr. Roy, can you just highlight if anything has been missed, and then we can wrap up the session.
No, sir, it's absolutely fine. I mean, you haven't missed anything. Rather, you have run the social session very nicely. And what we will have a small discussion after this. I request the participant may leave, and we, the session chairs, have a small meeting after that.
Sure. Sandeep Ghosh